Alright, let's take another look at a linear programming example here. For now, we're just looking at the standard maximum problem. Just know that in the next week or so, we will be looking at minimization problems as well. So we'll get to minimums. For now, we're just going to focus on maximums. Let's go ahead and identify the objective function. We are trying to find the maximum of z equals 3x plus 2y. And our constraints are given by these inequalities right here. So we're going to start by graphing the feasible region based on these inequalities that are the constraints. So let's start with 3x plus 2y equals 18. If x is equal to 0, then 2y will equal 18, and so y is equal to 9. And if y is equal to 0, then we get 3x equals 18, and so x is equal to 6. So let's go ahead and start graphing our feasible region here. We have a point up at 0, 9, so this will be up at 9, and we have another point at 6, 0. So let's go ahead and put that here, 6, 0, and we can connect our dots with a solid line. Let's go ahead and find which direction our feasible region is going to be. Oh, before I forget, you should always label your lines. 3x plus 2y equals 18. And the reason for that is because when we need to find corner points, it helps to know which line represents which function. So we've done our first one here, and we need to test a point to see which direction the feasible region is going to be. So let's go ahead and test the origin. So we would have 0 plus 0 less than or equal to 18. That is true. And so our feasible region is going to be pointing towards the origin. I'm only putting a couple arrows now just because I don't want the picture to get too cluttered, okay, because we are going to need to see the corner points, so that's why I only have a couple arrows here. Let's go ahead and switch to the next one. We have x less than or equal to 4, so x equals 4 would be a little bit to the left of 6, and we'll have a vertical line at x equals 4. And we want x less than or equal to 4, so that would be things on the left of this vertical line, okay? And we also have x greater than or equal to 0, so x equals 0 is the y-axis, and we want x values greater than or equal to 0, so our feasible region will point to the right, okay? So far, we can see it looks like the region is probably going to be in between these two vertical lines, and we'll see what the next two feasible regions give us. So looking at 2y less than or equal to 12, 2y less than or equal to 12 is equivalent to y less than or equal to 6. So let's go ahead and graph y equals 6. That'll be a little bit less than 9. Here's y equals 6. And we want y to be less than or equal to 6. So our feasible region is going to point down towards the x-axis. And last but not least, we have y greater than or equal to 0. So y equals 0 is the x-axis. And so if y must be greater than or equal to 0, then we want to point upwards. So our feasible region ends up being this shape bounded on all sides. So we have a bounded feasible region, which is good because we want corner points. So it's in between all of our shapes. So we see that we have a corner point at the origin at 0, 0. We have a corner point at 0, 6. I know the y value is 6 because the red line is y equals 6. We have a corner point right here that we don't know what the x value is, but we do know the y value. And we have another corner point over here where x equals 4, and we're not sure the y value there either. And finally, we have our last corner point at 4, 0. And again, I know that this is at 4, 0 because the x value has to be 4 and the y value is 0. So now let's go ahead and find our two missing corner points. I'm going to call this corner point, let's call it A and B. Okay? So corner point A, at corner point A, I know that the y value is 6. I also know that corner point A is on the line 3x plus 2y equals 18. because it's the intersection of 6 and 3x plus 2y equals 18. So we can go ahead and say 3x plus 2 times 6 has to equal 18, and then we can solve for x. So we have 3x plus 12 equals 18, and so 3x would equal 6, and so x is going to equal 2. So our corner point is at 2, 6. Similarly, we can do the same thing for b. So if we try to solve for corner point b, we know that the x value is 4, and we know that it has to also be on the line 3x plus 2y equals 18. So we have 3 times 4 plus 2y equals 18, and now we can solve for y. So 12 plus 2y equals 18, so we'll have 2y equals 6, and so y is going to equal 3. And so our point B is at 4, 3. And now we have all 5 corner points. Now that we have the 5 corner points, we can go ahead and evaluate the objective function at the corner points. So this is where we'll use a corner point table, or a corner point chart. So we'll have our corners listed. In this case, they are x, y, because those were the variables we're using. And then we have our objective function z, which is 3x plus 2y. And I'm getting the objective function from the beginning, right? That was in the problem. So let's go ahead and start at the origin. So at 0, 0, our objective function comes out to be 3 times 0 plus 2 times 0, which is simply 0. Let's see. I'm going to go, starting at the origin, I'll go clockwise. So the next one will be 0, 6. And so our objective function would be 3 times 0 plus 2 times 6, and we'll get 12. The next point we're at is a, so that's 2, 6. And so z would be 3 times 2 plus 2 times 6. And so let's see, that'd be 12 plus 6, which will be 18. Okay, so far so good. Let's see, the next point is b. That was 4, 3. So this should be 3 times 4 plus 2 times 3. That also is 12 plus 6, and so we also get 18. Interesting. And then our final point is at 4, 0, and so z comes out to be 3 times 4 plus 2 times 0, which is 12. So now we need to go ahead and look at the corner point chart and see which one has the maximum output. Well, what we see here is there are 2 points that have a maximum output. We have a maximum output of 18 at the point 2, 6 and at the point 4, 3. So this means that we have a case where we have multiple optimal solutions. And what that means is that any point that is on the line segment that connects A to B, so any point on this line segment here is a solution to our linear programming problem. And so the way we would say that is we can say that we have multiple optimal solutions. It's a bit of a tongue twister. Try to say that 5 times fast. Multiple optimal solutions. And we want to say that any point on the line segment, because technically a line keeps going forever, so on the line segment that connects, so connecting the point, let's see, 2, 6 to the point at 4, 3, it has a maximum value of, 18. Okay. So the maximum value that the function, the objective function ever attains is 18, but instead of occurring at only one point, it occurs at every point that's on that line segment. And so you want to make that clear in your solution. So there are multiple optimal solutions. Any point on the segment that connects those 2 corners is an optimal solution, and that value of the optimal solution is 18. So the maximum value of this objective function is 18.